Vectors. Coordinates in 3 dimensions. We saw how a point can be represented on a Cartesian plane or the XY plane. In 3 dimensions, we introduce another axis called the Z-axis. Our point is that represented as XYZ. Consider the figure below. The coordinates of the points are shown below. Column and position vectors. A column vector represents a change in position or displacement. For example, the column vector 2, 3, 1 represents a displacement of 2 units on the x-axis, 3 units on the y-axis, and 1 unit on the z-axis. The column vector 2, 3, 1 could represent a displacement from 583 to 352, that is 583 minus 352, which gives us 231. For example, find the column vector AB, where A is 2, 4, 3 and B is 6, 2, 8. In the solution, AB is given by B minus A, which is 6, 2, 8 minus 2, 4, 5, which gives us 4 minus 2, 5. When the displacement is from the origin, the column vector is called a position vector. That is, the position vector of a point Q 369 is OQ is equal to 369. Note that the position of a point is represented as XYZ. The vector of that point is represented as XYZ. Operations on vectors. Addition and subtraction of vectors is done in the same conventional way, that is, adding or subtracting the corresponding figures. If AB is 1, 2, 4 and CD is 6, 9, 1, then AB plus CD is shown as this. CD minus AB is illustrated as follows. For example, find the column vector AB if the coordinates of A are 3, 2, 4 and B are 5, 2, 7. In our solution, the position vector of point A is OA, 3, 2, 4, and that of B is OB equals to 5, 2, 7. AB is equal to B minus A, which is equal to 2, 0, 3. The vector is denoted using small letters, that is, OA is A, OB is B, and OC is C, etc. Magnitude of a vector. This is also called the modulus of a vector, and it is the length of the vector. Consider the point A on the figure below. Using Pythagoras theorem, OA is given by square root of 2 squared plus 2 squared, which is 2.83 units. The length OA is the modulus or magnitude of vector OA, and it's represented as such. In general, for a point Pxyz, the modulus of OP is given by square root of x squared plus y squared plus z squared. If PQ is equal to ABC is a vector joining point P and Q, then the modulus of PQ is equal to square root A squared plus B squared plus C squared. Example: given points P 2, 5, 1 and Q 3, 2, 6, state the position vectors of P and Q, find PQ and find the length PQ. Position vector of P is OP is equal to 2, 5, 1. Position vector of Q is OQ equals to 3, 2, 6. PQ is equal to OQ minus OP, that is 3, 2, 6 minus 2, 5, 1, which is equal to 1 minus 3, 5. Length PQ is given by 1 squared plus minus 3 squared plus 5 squared, square root of which gives us 5.83 units. Unit vectors. This is a vector with a magnitude of 1. In 2 dimensions, there are 2 unit vectors I and j, where in 3 dimensions we have I, j and k. These represent the points I, 1, 0, 0, j, 0, 1, 0 and k, 0, 0, 1. Test their magnitude to confirm that it is 1. The respective position vectors are given as follows. In a position vector, the x-coordinate is the coefficient of I, y-coordinate is the coefficient of j, and the z-coordinate is the coefficient of k. For example, if a point P has coordinates 4, 2, 3, it can be expressed in terms of the unit vector. OP is equal to 4, 2, 3, which is equal to 4 into 1, 0, 0, plus 2 into 0, 1, 0, plus 3 into 0, 0, 1. But replacing the columns with respective letters, we have OP is equal to 4i plus 2j plus 3k. Similarly, if the coordinates of Q are 5, 2, 9, then OQ is 5i plus 2j plus 9k. In general, a column vector ABC can be expressed in terms of the unit vector as AI plus BJ plus CK. For example, given that vector A is 2i plus 4j plus 2k and B is I plus 6j plus 4k, find 2a plus 3b and the modulus 2a plus 3b. In our solutions, 2a plus 3b is equal to 12, 26, 16. Modulus of that is 32.80 units. Parallel vectors. Consider the figure below. PQ is Q minus P, which is 3, 3. RS is S minus R, which is 6, 6. PQ is 3, 3 and RS is 6, 6. Clearly, RS is 2 PQ. The gradients of PQ and RS are equal. Therefore, PQ and RS are parallel. Generally, if a vector is a factor of another, then the two vectors are parallel. That is, if vector A is KB, where K is a scalar, then vector A is parallel to vector B, written as this. Collinear points. Consider the figure below. From the figure, PQ is equal to 1, 2. QR is equal to 1, 2. Thus, PQ is equal to QR. Therefore, PQ is parallel to QR because PQ is a scalar multiple of QR, that is 1. Point Q is common to both PQ and QR. In general, points are collinear if the vectors are parallel and the vectors have a common point. For example, show that A, B, and C are collinear. AB is 1, 2, BC is 3, 6. From the above answer, BC is equal to 3AB, that is 3 into 1, 2. Hence, AB is parallel to BC. Point B is common and thus point A, B, and C are collinear. Midpoints of vector. Consider the figure below. M is the midpoint of PQ. Find the coordinates of M. OM is equal to OP plus PM, but PM is a half PQ. PQ is equal to Q minus P, which is 1, 2, 3. OM is equal to OP plus a half PQ, which will give us 3.5, 5, and 6.5. The coordinates of the midpoint of vector PQ are 3.5, 5, 6.5. In general, the coordinates of the midpoint of a vector AB, where A, B, C, and B is D, E, F, is given by A plus D over 2, B plus E over 2, and C plus F over 2. Proportional division of lines. Internal division. Consider the line below. Line AB is divided into 4 equal parts. AC is a quarter of A, AD is a half of AB, AE is 3/4 of AB. In the ratio form, C divides AB internally in the ratio AC to CB equals to 1 to 3, or BC to CA is equal to 3 to 1. Equally, AD to DB is 2 to 2, which is equal to 1 to 1. Generally, a point divides a line internally if it lies between two endpoints, that is A and B. External division. AP is divided into 7 equal parts. AB is divided externally in the ratio AP to BP is equal to 7 to minus 3, or minus 7 to 3. Equally, Q divides AB externally in the ratio AQ to QB is equal to 5 to minus 1, or minus 5 to 1. AR to RB is equal to 6 to minus 2, or minus 6 to 2. The ratio theorem. Consider the line PQ. R divides PQ in the ratio 2:5. O is an arbitrary origin. OP is vector P, OR is vector R, and OQ is vector Q. OR is equal to OP plus PR, which is equal to OP plus 2/7 PQ. But PQ is equal to minus OP plus OQ, which is equal to OQ minus OP. OP is in opposite direction, and thus PO is a negative. Therefore, OR is equal to OP plus 2/7 into OQ minus OP, and thus R is equal to 5/7 OP plus 2/7 OQ. Suppose R divides the line externally. We shall have the figure below. R divides PQ externally in the ratio 5:2, and OR is equal to OP plus PR. Following the same principles, we have R is equal to minus 2/3P plus 5/3Q. Let's now consider the figure below. R divides PQ in the ratio mn. OP is equal to P, and OR is vector R, and OQ is vector Q. Following the same procedures, we'll find that OR is equal to OP plus m/m plus n into OQ minus OP. In summary, R is equal to n/m plus n times OP plus m/m plus n times OQ. Generally, the ratio theorem states that if a point R divides a line PQ in the ratio m to n, then the position vector of R is OR is equal to R, which is equal to n/mn P plus m/m plus n Q, where P and Q are position vectors of point P and Q respectively. Please note the following about the position vectors.
The importance and role of communications through broadcasting. I learned that.
Understanding the balance between vision and expression. I learned that.
Exploring the issues of our time. I learned that.
How to think like a great designer. I learned that.
Integrating creativity with professionalism. I learned that.
That's where I learned.